Finally, we reach the sine wave generation using the Taylor series. It is also a method that is widely used. It can be highly optimized, and this is the method that the DSP library from the Texas Instruments C5515 processor uses. But it's highly optimized for the processor, and it's written in assembly. But we will see how it works. So first, let's take a look at the first 5 derivatives of a sine wave. So for that, I'm importing SymPy. I'm defining some symbols and a function. So the first we are going to have our sine wave, so amplitude sine omega t. Then we will have the first derivative, the second, the third, the fourth, fifth, until the seventh. It starts repeating, so we don't need more than this. So when we pay attention, we will see this pattern. So we will have here, we have 1, then omega, omega squared, omega to the power of 3, 4, 5, 6, 7, and it will keep going. Then we have our sign changes. So we have the first derivative, then we have a sign change for the second derivative. Then we have continue this, but then we have a sign change for the fourth and fifth, and a sign change for the sixth and the seventh. And we also see that we have sine, cosine, sine, cosine, sine, cosine, sine, cosine. So when we observe this relation here and how it keeps going, we can see in terms of these equations. So when k is equal to 0, then we will have m equals to 0, and then we have our original function, it's here. Then k is equal to 0, but m is equal to 1, and we'll have the first derivative, omega to the power of m, and this is the cosine, and this is exactly what we have here. Then k is still 0, but m now is 2, and then we will have the second derivative, omega to the power of 2, and we have minus sine. Then we have k equals to 0, but m is equals to 3, so it's the third derivative, and we have this minus omega to the power of 3, and we have the cosine, and then k goes to 1, and we have m equals to 4, so it's the fourth derivative, omega to the power of 4, and then we have m equals to 5, k is still 1, we have the fifth derivative, and then we have the cosine, and so on and so forth. So we see this, that we will use this when we will implement this Taylor series. So the Taylor series is given by this formula here. So we have derivatives m, we have some factorial here, and we have this part here, which is x to the power of m. So we have something similar here. We have the derivatives, which will give us the sine and cosines. We have a factorial. So the Taylor series is very useful to approximate a function. So if we use some finite number of terms, we will get an approximation, and this is what we will do. We will approximate the sine using the Taylor series, and we will calculate, for example, when a is equals to 0, we will evaluate the function at point a. This is the nth derivative of the function. This is our Taylor series, and there is a special name for a when a is equal to 0, that this series is called the Maclaurin series. So as I said before, a function can be approximated by using a finite number of terms of its Taylor series. So we've seen the behavior of the nth derivative of a sine function, and now we can move towards its approximation using the Maclaurin series. So we will evaluate function when a is equal to 0. So for that, let's look at the first 8 terms. So if we calculate the derivative at t is equal to 0, so this is what we are doing here. So it will be 0, then a times omega, 0 minus a times omega to the power of 3, 0 a to the power of omega to the power of 5, 0, and so on and so forth. So what we're doing is, now that we'll plug in these values for the derivatives here, so m is 0, so it's the first derivative, the function, then the first derivative. So we will have already this value, so we can just plug in this series. So let's do this. Now we will have, if we will replace the values into this Maclaurin series that we have from the definition, and then we have here for the first part when m is equal to 0, so we will have t 0 here, t minus 0 to the power of 0. Then when m is equal to 1, we will have the first derivative at point a, 1 factorial, and x to the power of 1. And we have, that will be, in our case, t minus 0 to the power of 1. And we go this for all the values. So now we have for 0, this is equals to 0. But for 1, we have that's a omega t. So the derivative, first derivative is a omega. Then we have this factorial, it's 1 factorial. Then we have t to the power of 1. T to the power of 1. So we have here. Now, then we have the second derivative is 0. So we don't need to worry about this. But the third derivative is minus a omega to the power of 3. So we have here the minus a omega to the power of 3. Then we also have this t to the power of 3, t to the power of 3, and we have the 3 factorial here. So the 3 factorials here. And we do this for the others as well. But we know that the fourth, 0, 1, 2, 3, fourth is 0, and we have the fifth, this is 0, and we have the 7. So we will get all this when we replace, and we end up with this thing here. So now if we would have infinite coefficients here, we will get an approximation, a very good approximation of the sine wave evaluated at point 0, and we can use this to approximate a function. So we will approximate, we calculated at point 0, but if it's near 0, it can also work. So another way to write this is we can write the Maclaurin series expansion by this formula here. So in this case, for the sine of omega t, it will be the sum, this is the amplitude. Here we have minus 1 to the power of m, and we have this coefficients of omega t, and we have the factorials. So this can be further simplified if we take a look here. We have a dependency on the previous coefficients calculated. So this is the first coefficient, omega t. This can be written as a multiplication of the previous coefficient times this value. Then we have the previous coefficient, which is here, times this value, and then the previous coefficient times that. So we can also take advantage of the pre-calculated values, and we don't need to calculate everything. It's very important to have in mind that factorials, they can grow very fast, and we can have overflow. So we're dealing with 60-bit integers, and already if we calculate the factorials of 9 factorials, we get numbers that will not fit in our integers. So it's very important to try to optimize and to try to avoid these overflows. So if we, instead of using factorials, if we will use some simplifications, it makes life easier.